This is the outside trailer tow mirror force versus displacement tester, sponsored by Magna Mirrors. The reason for this tester being designed was to improve the current testing method, which currently is a non-permanent setup and takes very long to perform as well as set up the test. Since this is an engineering test, repeatability and accuracy are very important. Key specifications for this project. The first being force application. We have 50, 75, and 100 Newton loads being applied during the test. There is a tolerance of 1/2 Newton. Since these forces just need to be repeatable, there is no need for increased precision. Now going towards the test time, we have under 2 minutes. So this means for a single test of running a mirror against these loads 3 times and averaging them, it should be under 2 minutes. Now for the configuration swap, this means that going from one mirror to another mirror, or changing the configuration between tests such as the up direction and the down direction, or extended or retracted mirrors. For the displacement measurement, the tester needs to be able to measure up to 10 millimeters of travel at a resolution of 100 microns or less. Now, with this in mind, the tester has been designed to go beyond these. Currently, it can measure up to 15 millimeters of distance with a resolution of accuracy of 20 microns. As for the budget, $5,000 was allocated for this project. Key features of this project are that it's significantly less arduous in terms of the setup changes. Prior to this, the testing method was non-permanent and it required a lot of effort by the operator to set things up not only physically, but also to ensure the repeatability between tests, which was not great. Another thing is that it's easy to understand the user interface. With a simple button press, the test will run and the results will output to the display panel. This reduces confusion and also aids in repeatability. Next, the ability to test both directions in nominal vehicle position. By this, we mean both the up direction and the down direction, which will be explained in the next slide. The old tester was not able to measure in nominal vehicle position, so it had to lay flat on a table, which was not ideal. Finally, the overall testing time has been reduced by at least 67%. At times, this can jump up to 80%, depending on the mirror and the configuration that needs to be in. These pictures show the different configurations that the tester can be set to. The up position is on the left, and the down position is on the right. Up and down reference which way the force is being applied on the mirror while it's in nominal vehicle position. This video will highlight how the operator can change from an up direction test to a down direction test. Going over the subsystems, we have the C bracket, which is the aluminum fixture that holds the linear actuator as well as the laser displacement sensor. This is connected by the pivot fork, which holds these two pieces together and connects to the rigid L bracket. The L bracket is rigidly mounted to the slide table. The slide table is bolted to a steel tabletop to ensure there's no deflection. 4 bolts secure the pivot mechanism, which rotates around a shoulder bolt that is connected to a shaft. There is a rotation limiter that makes sure the device can only be rotated in a certain direction for a certain amount of degrees to ensure that the cables do not get tangled. Now moving on to the mirror side of the tester. On the left, you see the A-frame by itself without a riser. On the right, you see an aluminum riser supporting it. These are mounted to a steel tabletop to ensure minimal deflection and act as a rigid body. Vibration plates will be attached where the bolts are currently. Then a mirror can be attached to the vibration plate. This video goes over how exactly these systems work for mounting the mirror rigidly to this side of the tester. First, the correct hardware is chosen for the desired mirror. Certain mirrors require a certain riser, or some don't require a riser at all. Now, once everything is attached, including the vibration plate, the mirror can be mounted. Notably, you can both attach a left-handed and a right-handed mirror to the assembly at once. However, during testing, only one mirror needs to be mounted at a time. There is a rotation guide at the bottom of the riser or the A-frame, whichever is used. This allows the mounting hardware to be easily spun, so left hand or right hand can easily be changed to. So for the technology used in this project, notably the Keyence IL100 and IL1000 were used. The IL100 is a triangulation laser distance sensor. This measures at an accuracy and repeatability of around 20 micron. The amplifier is used to communicate better with the IL100 over the distances that the cables need to cover, as well as shows an output screen for troubleshooting. Next, we had a Fregeli linear actuator. These are automotive actuators and was quite well suited for the purpose of this tester. This actuator has a 2-inch stroke rated to 35 pounds, which is much more than the required 100 Newton force. Next, we have a compound slide table that moves in 2 axes, allowing for easy reconfiguration. We have an ESP32 microcontroller that is controlling all the parts. Finally, we have an RTEC load cell. This is rated to 50 pounds, well above the 100 newtons required. Each of these pieces of technology were incorporated in these pictures as shown. Mounting hardware was included with the laser displacement sensor as well as the actuator. The arms of the C bracket were specially designed to incorporate these features. The compound slide table can be used to readjust the mirror so that it is in the correct location. However, we are not actually moving the mirror as it is rigidly mounted on the other side. This is simply moving the C bracket which holds the instrumentation. This can be moved to a specified location on top of the mirror, as the laser displacement sensor has a laser pointer that points down onto the surface of the mirror that can be visibly inspected. The control panel is seen here. There are 2 buttons, notably start and stop. If there are any errors or issues with the tester, the stop button can be pressed. Otherwise, all the operator needs to do is press the start button. The start button will begin the testing procedure, which is 3 tests, which are then averaged on the final summary screen. The following 2 videos show 2 different tests for 2 different mirrors. The first requires a riser. The testing procedure is as follows. First, the tester will push on the mirror and calibrate the force sensor. Once the system is calibrated, 3 tests will be ran back to back to back. For a single test, the force applicator pushes on the bottom or top of the mirror at 50, 75, then 100 newtons, recording the displacement of the mirror head at each. 3 of these will be consecutively done. The average of these results are taken, and this is what is recorded by the operator. In terms of the major obstacles faced during this project, most of it was found in the design period. For the C bracket, the arm design was critical in making sure that the displacement sensor was able to read the measurements for all the mirrors as well. The other side of the C bracket, which holds the linear actuator, was also important in making sure that there was no movement and there was a rigid connection. For the table portion of the project, limiting displacements occurred during loading was important in making sure that the table did not flex, which is why there are thick steel tabletops connecting both the slide table and the mirror side mounting hardware. For the pivot system, making sure the wire routing and rotation limiter were designed correctly was important to ensure that the components would not have issues with the wires being tangled. For the build portion of this project, part fitment and leveling the table surfaces took a long time. Circuitry was another obstacle we faced. There were many changes that eventually had to be made. And finally, some lessons learned from this project. First, backup parts being readily available in case of accidental breakages or when experimenting with new concepts is crucial. There were multiple times when we had parts break, notably electronics, not so much mechanical features. Another one was each part bought should be fully understood in terms of how it works before being put into operation. This was big for the load cell as initially we didn't understand quite what it was outputting, so it took a little while to figure out. Finally, having both mechanical and electrical on the same page really makes sure that the design is acting as it was intended and the results are getting the correct values.